Yesterday, I showed you what the purpose of this chapter is, right? To take weird functions and approximate them with polynomial functions. I also showed you how we're doing this. What we're doing is, if I have some weird function, okay, I choose a point that's going to be the center of my approximation, and then I build my polynomial approximation about that point. I can find a first order approximation. That would be a tangent line. And you go, okay, well that tangent line's a good approximation for a small neighborhood about that point. But if I want, I can not just have the functional value and first derivative of my polynomial approximation equal the functional value and first derivative of this graph. I can also have the second derivative of my the second derivative of my weird graph be the same as the second derivative of my polynomial approximation. Then I might get something like this, which is an even better approximation. It works for a larger, although what I did kind of didn't, but it supposedly works for a larger neighborhood. And then I could get a third degree approximation, and maybe the third degree approximation would work for an even greater, neighborhood about that point. And as I add each degree of approximation, my polynomial approximation gets better and better. Hey, that's what this is all about. And I showed you the long way to do that stuff. Well, now I'd like to show you a quick way to do it, where I just give you a formula and you work with the formula. And rather than me writing it on the board, I'm just going to show you my notes. And I'm going to wait till the light comes on. And then you don't have to write this down. I just need you to look at it, and be aware of where this all comes from. So Brandon, would you be a dear and turn off the lights, or turn off the one switch? Thank you. Okay, this is my notes. This is my handwritten notes. Back when I was young and I had good handwriting. So I'm going to ask you to essentially start reading here. Now we're ready to derive the formula for the approximating polynomial centered at any point x equals c. And this is called a Taylor polynomial. Do you remember what's special about a Maclaurin polynomial?
Centered at x equals.
Yeah, centered at 0. So it gets its own special little name. It's centered at 0. But a Taylor polynomial is the approximating polynomial approximated anywhere. And so what I do is I say, okay, I'm going to get an nth degree approximating polynomial. So it's going to be a0 plus a1 times x minus c. Remember, if we're going to be centered at x equals c, we need all these terms to be x minus c squared and to the third and to the fourth power. So we get that incredibly convenient scenario where you stick in c and all of the terms with x's go to 0. It makes it real easy to find those coefficients. Okay? So once I got my nth order polynomial, I'm going to take the first derivative. So now I got a1 and 2a2 x minus c and 3a3 x minus c squared and 4a4 x minus c to the third. I take the first derivative all the way to n times a sub n x minus c to the n minus 1. Then I take the second derivative, and I want you to see what starts happening with these coefficients. This coefficient is 2, but this guy became 2 times 3. And this guy becomes 3 times 4. And the next one would be 4 times 5. And so on, all the way to n minus 1 times n. Then I take the third derivative, and now I've got 2 times 3 here, and I got 2 times 3 times 4 there. And I'd have 3 times 4 times 5, etc., all the way to here, and then I get my fourth derivative, and now I've got 2 times 3 times 4. The next term would be 2 times 3 times 4 times 5, you see? And this guy will be what that is. And so when I finally get to my nth derivative, I'm going to have 2 times 3 times 4 times 5 times 6, all the way to n. Okay? So I want you to see immediately that my coefficients of these the coefficients of these coefficients, the numbers in front of A1, A2, A3 is the factorials, right? This is 1 factorial, this is 2 factorial, this is 3 factorial, this is 4 factorial. If I got down to A5, which I don't show, it would be 5 factorial times A5, all the way to A sub n, which is n factorial. So now I'm going to line up the functional values and the derivatives. Let me see what I get. Alrighty. And so I get this sort of thing where, remember, this guy had this guy had 2a2. So a2 ends up being f double prime of c over 2, because I need f double prime of c to equal the second derivative of my approximating polynomial when I stick c in. So this guy ends up being f double prime of c, and this guy ends up being a2 over 2. This guy was a3, this is a3 over 3, I'm sorry, this guy is 3 factorial times a3, so a3 ends up being f triple prime over 3 factorial. Remember yesterday how those coefficients were 2 and then 6, and then if I'd gone further, 24? You know, so you're just getting your factorials. And so based on the fact that all of these guys end up having the functional value or the derivative values divided by the factorial, I end up with this. This is my Taylor polynomial right there. That's the general formula for the Taylor polynomial. It's just, you know, now I don't have to go through this process anymore. I know that the constant term will always be f of c, and I know the first order term will always be f prime of c times x minus c, and so on. You know, this is always a naught, this is always a1, this guy here is always a2, all the way to this guy being a sub n, you know? Well, that's where it comes from. Any questions or issues before I write that formula? I'm going to write this formula on the board, and then we're going to spend the rest of the period just working with that formula. Okay. And if you're wondering, again, where did the factorials came from? It came from the fact that I had to take multiple derivatives. And when I have something to the 5th power and I got to take 5 derivatives of it, I end up with 5 times 4 times 3 times 2 in front of it, you know? That's where it comes from. Well, if you don't get it perfectly, that's okay. Hey, Brandon, could you turn on one light? And now let's go ahead. I'm going to write down the Taylor polynomial, or what they call Taylor's theorem, or a part of Taylor's theorem. And then we're going to work with it. Here we go. Okay. Taylor's theorem. We can approximate f of x with the nth order. And when I say nth order, I also mean nth degree. That's the, you know, the highest exponent term. Okay. We can approximate f of x with the nth order polynomial p sub n of x, centered at x equals c, as follows. Okay, here it comes. F of x is approximately equal to f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared plus f triple prime of c over 3 factorial times x minus c to the 3rd power plus dot dot dot, all the way to the nth order term, which would be the nth derivative evaluated at c over n factorial times x minus c to the n power. And that's my approximating polynomial. I'm going to show you a problem where I do it, and then I'm going to give you guys a problem to do, and then another, then another, then another, until you just get sick of it. Here's example number 1. Get fourth order approximating polynomial of f of x equals e to the x, centered at x equals 0. What's the only figuring I have to do here? What's the only thing that I need to take action to find? Yeah, the derivatives. All I need to do is find what f of c, f prime of c, f double prime of c, f triple prime of c, etc. are. I don't have to do anything else. This x stays x because it's a polynomial. I need x's there. And my c, I know it, it's 0. You see what I mean? So the only figuring you have to do on these problems is to find the functional value and all of its derivatives. So you see, the act of doing these problems actually isn't that difficult. Hey, let's go for it, okay? F of x equals e to the x. F prime of x equals e to the x. F double prime of x equals e to the x. How far down should I go?
The 4.
Yeah, fourth derivative, because they asked for the fourth order approximation. So I'm going to need the fourth derivative. F double triple prime is e to the x. The fourth derivative is e to the x. Great. Now I need to find all of those values. I need to find what f of 0 is, what f prime of 0 is, what f double prime of 0 is, etc. I'll just use 4 little slashes instead of the Roman numerals. Some books like to use the Roman numerals. Okay, well, of course, there's a reason I chose e to the x, right? Because each one of these guys is 1. Boom, 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 boom. And so I can say that f of x, which is equal to e to the x, is approximately equal to 1 plus 1 times x, because my c is 0, plus 1 over 2 factorial times x squared, plus 1 over 3 factorial times x to the third, plus 1 over 4 factorial times x to the fourth. And there it is. That's my approximating polynomial. That'll get me a real good approximation in a neighborhood about 0, yes?
Why did you do the exclamation marks?
Because that means factorial.
Oh.
Those are factorials. That's the same as 2 times 1, that's 3 times 2 times 1, that's 4 times 3 times 2 times 1.
Oh.
So if you wanted to write it out in a way that it's easy to put in your graphing calculator, then yeah, you would do this. You'd go like that.
Oh.
I'm assuming that you guys know what factorials mean. Ouch. How many people here have never done factorials before? Oh my God. Oh, you poor. Oh, that would be like me asking, does anyone know who the first president of the United States is? And like no one knowing. What's that? Oh my God. You poor kids. Well, first of all, factorials only apply to integers. And 12 factorial is 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what factorial means. You guys okay with that? So you guys never did factorial, huh? You never did like permutations and combinations where you had to name like factorials? Oh man, you guys are so, it's like, you know, wow. Now, have you been told that Santa Claus isn't real?
No.
No? Okay. Oh my God. You poor deprived kids. Okay, it's time for you guys to do a problem. Here we go. Example number 2. Get, just 1 second. Get third order approximation of f of x equals sine of x centered at x equals 0. Good luck. Please do this now. I'll give you a hint. Please do write down all your f's and f prime and f double prime, and then stick in 0, and then plug into the formula. Good luck. Or maybe, hey, you know what? Can I ask for the fifth order? Let's go fifth order. Yeah, because I want to actually do something else with this.
Mr. Sheena,
Yes.
here's my pass.
Okay. I'll take your forged pass. Thank you. I don't even know, who is this person?
From the discipline office.
Discipline? What, you were being disciplined?
No.
What'd you do wrong?
That's what I'm doing right. Did you guys get that far? Okay, then, hey, let's plug it in. Are you guys okay that the first term is 0? So I got 0 plus, then the second term, f prime, is 1. So I got x. What's the next term? Hopefully you're getting 0, because f double prime is 0. Then the next term is negative 1. The next term is 0. And then the last term is 1. I know I went pretty fast, but how many people got that? Okay, just like 3 or 4 of you. So we're going to have to do many more. Is there any question or problem on this? Okay. And so I can simplify it, of course. Sine of x is approximately equal to x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. Alrighty. Here, we can even see how good of an approximation that is. Let me get my... Oh, I found a new bulb for my precious overhead projector. All right, hey, let's see how good an approximation that is. So here I've got sine of x, and I better be in radians mode, good. And down here I'm going to put x minus x raised to the third power divided by 6 plus x raised to the fifth power divided by, if I don't know what 5 factorial is offhand, I can press 5 and then press math and then probability of all things and then go down to number 4 if you have my calculator here. Okay. And so now I'm going to go like from negative pi to pi. And I'll go from like a -2 to 2. And here we go. Well, that smells burny. Okay, so can you see?
Wow.
You smell that burning dust? Yeah. It's like it's as if it's a brand new thing, but it's, I mean, the bulb is new, but that's it. Well, anyway, are you guys okay that this appears to be a reasonably good approximation from, you know, approximately they're a little bit more than 2, -2, all the way to a little bit more than +2. Then it starts diverging, then it goes away, you know? And of course, if I showed you more of the graph, it would become even more obvious to you, you know, that if I went from -6 to 6, and this went from -20 to 20, then here comes my sine graph, and here comes my, you know, 5th degree graph, and you can see that, you know, we get to the point where that there's no relationship between the 5th degree graph and the sine graph. But you know, for that one region, it was pretty good, you know. -3.2 to 3.2, -2, or how about we go -3, okay, clear, -3 to 3, you know. But for that region, it's a pretty good graph, you know.
So, Mr. Shane,
Yes.
if you do like infinity to infinity, so like it was f of n, so it'd be like f to the infinity power times like, or like, so it'd be always 1, right? Is there a way to do it so that it would be the exact same graph?
Yes. Tell me, if I wanted my polynomial approximation to be really accurate from -infinity to +infinity, what would I need? Infinite what?
Oh, infinite knowledge.
What's that? Infinite what?
Order.
Yeah, infinite order. I would need an infinite number of terms, right? That would get you there. And it would. It totally would get you there. Now, that kind of defeats the purpose of a polynomial approximation, but sometimes that's what we want. Sometimes we're okay with an infinite number of terms. Absolutely. Well, there's something I can do to make this a better approximation right now. What could I do here to make this a better approximation? Like, can you see what the next term should be? What should the next term be?
X to the 7th over 7.
Over what?
7 factorial.
Yeah, x to the 7th over 7 factorial. And should that be a positive or negative?
Negative.
Yeah. So you guys get the what do you call it, the rhythm of it, right? You get it's very easy. Right? Here, notice this approximation is good from -2 to +2. Well, now I'm going to put another one there. I'm going to go function y2, and then I'm going to add that term, or subtract rather, that term you just gave me, x to the 7th power divided by 7 factorial. Okay, and let's see how much better this is. Boop. This approximation, wow. It's looking good from like -3 to +3. Here, let me change the window. -4.5 to 4.5. Let's go with that, you know? And then let's go like -5 to 5, just so you can see it better. So here's my sine curve. And then here comes my 5th order approximation. Alrighty. And here comes my 7th order approximation. Yeah, and so I hope you see my 5th order approximation is good from like about right here to about right here. That's my 5th order. My 7th order is good from there, so like 3.5 to -3.5 to +3.5. So I just want you to see it. And the more terms I add, the larger the neighborhood over which my approximation is a good approximation. You know? You guys okay with that?
So here's the next thing. I'm not going to teach it to you yet. I'm just going to demonstrate it to you. You can get the general term, okay, plus dot, 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 plus, and I'm going to show you the general term. Let's say I told you that this guy here was the 0th term, and this guy was the first term, and that's the second term, and that's the third term. Then what power would my x be to if I wanted like the nth term? What I'm trying to do, let me just show you. Okay, this is x to the first, by the way. You guys okay that if I tell you which term it is, you can get the exponent by just taking this guy, doubling it, and adding 1? So my nth term would be to the 2n plus 1 power, and the factorial would be to the 2n plus 1 factorial. And then finally, because I have to switch signs, I have to have -1 to the, and to the 0th power I need it to be positive, to the first power I need it to be negative, second term needs to be positive, so I would just go -1 to the nth power. So that my 0th term would be positive, my first term would be negative, my second term would be positive, etc. So there's a term for this, it's called the general term. Okay? Well, hey, I need to give you more problems. Okay, are you guys ready to do another one? Do one on your own.
Sure.
Good, thank you. Thank you for saying sure. I now want you to get the 5th order approximation of the sine of x centered at, oh, just a second. It'll be centered at pi over 2. So it's going to be that problem, but only centered at pi over 2, not at 0. So please do that now. So please do the same thing, but center it at pi over 2. And at this point, I am going to walk around and see if you guys are doing it. What's that? The equations, the Taylor equation? Here's the Taylor equation. F of x is approximately equal to f of c plus f prime of c plus f double prime of c over 2 factorial times x minus c squared, etc. Just goes like that. I hope everyone is starting off by getting all of your functional values and derivatives. Okay, cool. Good for you. Cool. Yeah, there it is. Good for you. Cool. Great. Beautiful. Okay, good. Right now, the functions. Yeah, good for you. Thank you for not chewing gum this morning. Yeah. Oh, you are?
Yeah.
Oh, okay. And don't forget, it's x minus pi over 2 now. X minus pi over 2 to the square, x minus pi over 2 to the 4th. All right, good for you. Great, but it's got to be x minus pi over 2. You're centered at pi over 2 now.
Oh, right.
You're not centered at 0 anymore. Good, beautiful. So, so good. Great. Yeah, you got some bad sines and cosines going on there. The sine of pi over 2 is 1. Cosine of pi over 2 is 0. You're thinking like it was pi over 4. You made the problem harder than it needed to be.
Good for you. Good for you. Good for you, Taylor. Now, we're doing pi over 2, right? Oh, yeah, okay. Yeah, you're good. Wait, what? I'm confused. Oh, I missed that one. Okay, you're good.
Okay.
I look like... Yeah, looking good. Now you're ready to just write that up, x minus pi over 2. Every term is going to have x minus pi over 2 in it. Good, good. Okay, I'm going to get caught up to you guys. Okay, yes?
Do we see x minus c for f minus c? In the previous.
Yes. Oh my God. Yes. I blame Omar. Because you asked me to write it up there again, and I wrote it up wrong. And I never would have written it up wrong if it hadn't been for Omar asking me to write it up again.
That's on you, buddy.
Well, you know, I'm trying to shift the blame. I'm trying to be presidential. Okay, so yes, Lauren, you are correct. My bad. My total bad. Everyone in video land will be aware of that. So now, you know, here's y equals sine of x, but now I'm going to be centered at pi over 2. So I got 1 minus 0.5 x minus pi over 2 squared, and then plus 1 divided by 4 factorial. Whoops. Times x minus pi over 2 raised to the 4th power. And so I'm going to graph them, and here's my sine graph. And here comes my 4th degree approximation. And so I want you to notice now that my 4th degree approximation is a really good approximation from there to there, right? From negative about a half to 1, 2, 3 to positive 3.5. What's the center? Pi over 2, you know, 1.57. That's now the center of the neighborhood over which my guy is a good approximation. Yes?
So is the 4th and the 5th order approximation the same because the last one is 0?
Leilani asks, are the 4th and 5th order approximations the same because that last term is 0? And the answer is yes. Yes. So all you're going to get, if someone asks for a 5th order approximation, all you can give them is a 4th order approximation because the 5th order term is 0. Yeah, good for you. And by the way, you know, this next term would be 1 over 6 factorial times x minus pi over 2 to the 6, right? So again, something I'm not teaching you yet, but you are going to have to be able to find the general term eventually, where if this is the 0th term, this is the 1st term, that's the 2nd term, and that's the 3rd term. Now I can say this is negative 1 to the nth power times x minus pi over 2. And you tell me, what should my exponent be now for the nth term?
2n.
Yeah, 2n. Good for you guys. 2n. And this guy? 2n factorial. Yeah. And like I said, you'll be asked to do this sort of thing like in about a week. But right now, don't worry about it. Okay. Hey, any questions or problems on this? Okay, then hey, let's keep going. You know what Michael Jackson says? Don't stop till you get enough.
What is it?
Well, when the period ends, that's going to be enough. Okay. Here's one of the perks of this Taylor approximation thing, okay? What if I told you, I don't even know what the function is, right? What if I said, I don't even know what the function is, but I do know some values of the function. I do happen to know that f of 0 is equal to 2, f prime of 0 is equal to 4, f double prime of 0 is equal to 5, and f triple prime of 0 happens to be negative, I don't know, negative 7, okay? Let's say I told you this. So I don't even know what the function itself is, but I do happen to know its functional value and its derivatives at 0. Could you get me a third degree approximation of f of x? Even though you don't even know what f of x is, could you get me a third degree approximation of it? No. The answer is yes, and please plug into this formula now.
But you don't have C.
Yeah, you do. What is C?
0.
Yeah. Since that's what all the functional values they give me are, it's going to be 0, yeah. So please do that now. It is centered at 0. Do you mind if I just call 3 factorial 6? Okay, how many people got 2 plus 4x plus 5 halves x squared minus 7 6x to the third? Yay, right? Good enough for those of you who got it. Any question or problem on this? And so, again, I don't know what the function is, but I can get an approximation of f of 1. You tell me. What's f of 1 approximately equal to? How am I going to get an approximation for f of 1? Yeah, plug it in. F of 1, that's going to be equal to p of 1, which is going to be 2 plus 4 plus 5 halves minus 7 6, you know, whatever the heck that is, right? That's my approximation of f of 1. And since this is a third order polynomial approximation, this is probably a really good approximation. Again, even though I don't know what the function is, I do have a sense of what f of 1 is approximately equal to. Just stick that into my polynomial approximation. You see what I mean? So you're going to get a couple of problems on tonight's homework. This is number 16 and 17, where you're going to have this knowledge. And by the way, you know, this is my polynomial approximation for f of x, right? F of x is approximately equal to this. Could you give me an approximation of f prime of x? What is f prime of x going to approximately equal to? Someone, Carly, what should I do?
Take the derivative.
Sure, thank you very much. Take the derivative of f of x. So f prime is going to be approximately equal to 4 plus 5x minus 7 over 2x squared, right? That's the beauty of having polynomial approximations. It's incredibly easy to take derivatives of them. So if someone wanted f prime of 1, you know, hey, f prime of 1 is approximately equal to this, you know, 9 minus 3.5, which is what, 5.5? Yeah. So like I said, 16 and 17 go like this. They just give you the functional values. You don't even have to do any work. They just give you the functional values, and then you use them. Here's the last thing I got to teach you, and it's actually pretty easy. Just 1 second. Okay, good. Alrighty. So, centered at x equals 0, we found sine of x, right? Wasn't that the one we did? Sine of x? Because I departed from my notes. And what did sine of x equal? Was that the odd function, right? X minus x to the third over 3 factorial plus x to the fifth over 5 factorial plus or minus dot dot dot. Remember this? What if someone asked for an approximation, polynomial approximation of the sine of 2x? Well, there's two ways to do this. One way would be to start with f of x equals sine of x, or sine of 2x rather, f of x equals sine of 2x, and then get my repeated derivatives. But that's kind of a hassle, and you'll notice with each derivative I'm sprouting another 2, you know? But that's a hassle. There's an easier way to do this. I'm going to show it to you right now. Are you ready? If sine of x equals x minus x to the third 3 factorial over plus x to the fifth 5 factorial, then the sine of 2x is going to equal 2x minus 2x to the third power over 3 factorial plus 2x to the fifth power over 5 factorial. You see that? That's another one of the beauties. Yes, Brandon?
Oh, for derivative of f of x, why is it negative 2 plus 1?
Oh, I wasn't thinking. Thank you, Brandon. My bad. I wasn't thinking. It's positive. But that's the thing I want to teach you. Now, once you find the polynomial approximation of the sine of x, you got the polynomial approximation of the sine of anything. You just stick that thing in for x. So like, hey, let me give you one. Do you remember how e to the x, do you remember how the functional value and all its derivatives are 1? So that e to the x is 1 plus x plus 1 over 2x squared plus 1 over 3 factorial x to the third plus 1 over 4 factorial x to the fourth. Okay? Do you remember that? I'd like everyone right now. Oh, and by the way, this is a approximation. I'm feeling stressed because I'm running out of time, because we're out of here in 2 minutes. What if I wanted e to the x squared? Someone tell me in words, how am I going to get that? I certainly don't want to be taking a million derivatives of e to the x squared, because I'm going to sprout a 2x and then I'm going to have to do product rule the rest of the way. What's the easy way to get a polynomial approximation of e to the x squared? Nope. What's that? Nope, don't square every value. Remember how to get the sine of 2x, I just removed every x and substituted 2x in its place? Now if I want e to the x squared, what should I do?
Substitute x squared.
Thank you very much, Fatima. Yeah, substitute x squared for every x. This is now going to be 1 plus x squared plus 1/2 x squared squared plus 1 over 3 factorial x squared to the third. You see what I mean? All you got to do is substitute x squared for every x. Plus dot dot dot. And then finally, the last thing, what if someone wanted this? X e to the x squared. Okay? Well, we got e to the x squared. How am I going to get x e to the x squared? What should I do now? You know, I mean, I got this guy right there. What would you recommend I do now? Yeah, thank you, Brandon. Multiply by x. This is going to be x times 1 plus x squared plus 1/2 x to the fourth plus 1/6 x to the sixth plus 1/24 x to the eighth plus dot dot dot, right? which ends up getting me, oops, x to the third plus 1/2 x to the fifth, etc. All right, so, hey, good luck on tonight's homework. You're going to be doing nothing but this sort of stuff, just working with Taylor's theorem.